In this video, we're going to talk about visualizing what the singular value decomposition does graphically. So let's let A be a 2 by 2 matrix that has this singular value decomposition, U times sigma times V transpose. So in general, what A does graphically may be something complicated. So A might sort of represent a complicated process. But what U, sigma, and V transpose do individually are really simple graphically. Okay. So if we think about the transformation that A performs, we can do the same thing if we sort of break it up into these pieces. So first, we have to do V transpose, because V transpose is what would sort of multiply the vector x. If there was a vector x here, V transpose would multiply first. I don't want to erase that word. Okay, and then second, we would do what sigma represents. So second, we would deal with the sigma. And then third, we deal with U. Okay, so I have a picture sort of visualizing each of these steps. All right, so in this picture, so I'm beginning with a unit circle here. So if we think about what this matrix V is going to do, actually that's obscuring it kind of, let's erase that. So if we think about what the matrix V is going to do, V is going to map this vector E1 onto some vector. So it'll transform E1 to, let's say, to V1. And then it's going to transform the vector E2, the second standard basis vector, to a vector V2. So that's what the matrix V will do. So notice one of the things about this is that V is rotating these vectors. It's either going to be rotating them or reflecting them. So this is either a rotation or a reflection. So the same thing is going to be true about V transpose. So V transpose, so we've seen before that an orthogonal matrix is either going to be a rotation or a reflection. So V transpose is doing the inverse of what V is doing. So it's taking these vectors V1 and V2 and it's mapping them back to E1 and E2. No, I don't know what happened to E2. Let's go ahead and write it back in. So E2. So V transpose, the first thing that's happening here is it's either a rotation or a reflection. That happens first. Then we're ready for what sigma is going to do. So what sigma is going to do is it's going to scale these vectors in the unit circle. So it's going to take E1 and it's going to scale it. It's going to scale it by some amount. So it'll scale it and we'll end up getting sigma 1 times E1. Because remember, the matrix sigma consists of those singular values like sigma 1 and sigma 2. So E1 is getting scaled by that first singular value. All right, so in the same way, that matrix sigma is going to scale E2 by a factor of the next singular value, sigma 2. So notice it's taken this unit circle and now sort of stretched it or shrunken it into an ellipse. All right, so that is what this matrix sigma is doing. Sigma, this is scaling. This is scaling vectors. All right, so finally we have one more step. We have the step where now we multiply by U. So actually before we talk about that, let's go ahead and write down what sigma was doing here. Sigma was scaling vectors. So that's the next step. So now finally we're going to talk about U and what U does. So U is also an orthogonal matrix. So it's going to rotate or reflect vectors. So it's going to take this gray vector, sigma 1 times E1, and I've just gone ahead and rotated it. So when it rotates, now we will get sigma 1 times U1. And then sigma 1 times U1, we've seen before that that's the same thing as A times the vector V1. And similarly with the other basis vector, so that has also gotten rotated. So the result of the rotation, that is sigma 2 times u2. And we've seen before that that is a times v2. All right, so this step where we multiply by u, this is also either a rotation or a reflection, because multiplying by an orthogonal matrix either is a rotation or a reflection, or a combination of the two. So we finally end up rotating or reflecting for this final step when we multiply by u. So visually this is nice because we can think about a matrix A in terms of these three parts. V transpose performs a rotation or reflection. Sigma will scale vectors, either enlarge them or shrink them, and then u is going to rotate or reflect them again. All right, so I want to end this video by stating a theorem, or a key fact, essentially. Okay, so this fact talks about the biggest the length of A times a vector x can be, such that the length of that vector is 1. So this is saying that x has a length of 1, so it's on the unit sphere. So if we were talking about R2, this would be the unit circle. If it was R3, it would be the unit sphere. If it was a higher dimensional thing, that's called a unit. I'm still going to be referring to that as a unit sphere. So that's what I mean when I say the length of x is 1. So it turns out that the maximum the length of A times a vector x could be, when the length of that vector x is 1, it happens to be when this vector x is v1, where v1 is an eigenvector of A transpose A that corresponds to the largest singular value. The largest singular value, sigma 1. And in fact, with that specification, A times v1 will be sigma 1 times u1. So we have the length of this. And u1 is a unit vector. So this is a unit vector. So what we end up with when you take the length of sigma 1 times u1 is the sigma 1 we can sort of pull outside of this norm. And it doesn't even need an absolute value because sigma 1 is non-negative. So we end up with sigma 1. And the length of u1 is 1, so we don't need to write that. So that's interesting. This is saying the maximum that the length of A times x can be is the largest singular value, sigma 1. And in this picture here, that's what happened visually. If we think about where v1 was in this initial picture, here was v1. By the end of these three steps, this circle, this consisted of all the vectors x that had length 1. That was this, in this case, this unit circle. And by the end, it had gotten mapped to this ellipse. And the largest any vector was on the ellipse was this right here. It was A times v1. And that's what this fact is stating. To prove this, we would need some theory from section 7.2 and 7.3, which we haven't covered.